Please take your seats. Hello, everyone. I'm the session chair of this first session of the afternoon. We'll be going to hear 4 very exciting talks about satellites and networks in space, which seems like a very exciting topic. I don't know much about this topic, so I'm looking forward to learn more from the speakers. So the first talk is from the presenter will be Yuyu. Yuyu is a researcher at the Institute for Network Sciences and Cyberspace from Tsinghua University. His research interests lie in new satellite networking, edge caching, and content delivery optimization for next-generation space terrestrial Ethernet infrastructures. He has previously published at top venues including www and APNet. All right, so with that, I'll pass my mic to you.
Good afternoon, everyone. I'm very glad to present our work, SCOPE, a spatial and temporal collaborative cache and proactive transfer framework for low Earth orbit satellite networks. The core idea of this work is to rethink satellite content caching jointly in 2 dimensions. Spatially, we organize the satellites into latency-bounded collaboration groups so that the isolated storage can be pooled. And temporally, we proactively migrate high-value content from leaving satellites to entering ones during the handover window, so users never feel the cold start. I will walk you through the motivation, the design, and the evaluation. This presentation is organized into 4 parts. First, I will introduce the background and motivation, especially why isolated caching breaks down under the high mobility of LEO satellites. Then I will present the design of SCOPE, including its spatial collaboration and its temporal proactive transfer mechanism. After that, I will show our evaluation results from 3 perspectives: robustness, service continuity, and cost efficiency. Finally, I will conclude the talk and discuss the related work. First, I introduce why LEO constellations are promising substrate for satellite edge caching. Compared with GEO systems, LEO offers lower latency and higher through output, and modern satellites increasingly have onboard storage and computation. Then I explain the core problem. Because LEO coverage shifts every 3 to 4 minutes, terrestrial CDN strategy cannot be directly reused. Every handover may replace a warm and region-relevant cache with a cold or irrelevant one, creating the cache island effect. Finally, I point to the Starlink snapshot on the right. The constellation is dense enough that many neighboring satellites are connected through ISL inter-satellite links, so resource pooling is physically feasible. This leads directly to SCOPE. We lead spatial collaboration among nearby satellites and proactive transfer before handover, instead of treating each satellite as an isolated cache. Our second observation is about high temporal dynamics. We analyzed the Starlink Shell 1 trace and recorded satellite enter and leave events for different ground regions. As you can see in Fig 3, between time equals 6 minutes and time equals 7 minutes, a batch of warm satellite leaves regional cache. Its ratio suffers from a decline, from 32% down to 30%. Exactly as those region-relevant satellites depart, without intervention, the entering satellites stay cold for a long passive recovery period, during which users have to first data from the ground CDN, sharply increasing access latency. Crucially, and this is the key insight, the leaving and the entering sets actually coexist for a brief window, roughly 30 seconds. This temporal overlap gives us a concrete chance to execute proactive cache handover before the physical link breaks. We will explore exactly this window in our design. Identifying the handover window is only the first step. We must also make sure we use this limited time efficiently. Our design is motivated by 2 key asymmetries between leaving and entering satellites. The first is content value asymmetry. User records follow a CPS distribution, meaning a small number of items receive most of the records. Leaving satellites have served the current region for some time. hold exactly means high-value region-relevant items, which were identified through historical traffic. The second is regional relevance asymmetry. Entry silence, on the other hand, typically carry content that was popular in the previous service region, which is largely irrelevant to the new hotspot, that the storage is essentially wasted. Those two asymmetries together drive our value award spatial and temporal migration strategy. During the brief handover window, push high-value content from leaving silence to suitable entering ones, so the new silence arrive warm rather than cold. Welcome to part 2, the design of scope. After establishing why standalone caches in LU suffer from cache and cold start dips, we now show how scope addresses both. Design unfolds along two coordination dimensions: spatial cooperation with via latency-bounded clicks, and temporal continuity via value-aware predictive migration. We will close with the three-phase content retrieval workflow that ties everything together. Fig 5 shows the scope architecture. The ground segment runs the scope controller, which has two logical models. Member management decides how salads are grouped into cache clicks and which salad should transfer cache content to whom. Cache management runs on each satellite, handles local queries, and executes the transfers. A user request follows a three-phase retrieval workflow. First, from the local cache, then a cooperative inter-salad lookup, and finally a ground station fallback to the original ground station. This split lets the heavy planning live on the ground while salads only execute lightweight decisions. The first design decision is who can cooperate with whom. We model the visible constellation as an inter-salad link graph and keep only edges whose one-way latency stays under threshold. Any valid cache group must therefore be a click in that graph, so that every member can reach every other member within milliseconds. Although click elimination is NP-hard 0, the SO graph is fast and short diameter. So a brown crossbench search with orbital browning finishes within seconds for starting scale toplet. The right hand shows the idea. The orange triangle is one such latency bounded click. Unlike terrestrial CDNs, LU salads move on deterministic orbits, so scope handovers from a reactive event into a planned one. The controller projects each salad footprint onto every group region using TLE two-line elements, obtaining an end time and leave time for every salad group pair. Before a leave event, while leaving and entering salads will still overlap. Scope schedules migration job. The key is not to migrate arbitrary bytes. Scope scores cache objects by popularity, remain time to leave, and locality. Then transports only the top key value objects and skips stealth tuning expiring content. In this way, the overlap window is used for value-aware migration rather than bandwidth wasting replication. Putting space and time together gives us the user visible workflow. Every request works through three phases. First, the sender checks its own cache. A hit is served in a single hop. On a miss, phase 2 queries the rest of the cache group over intercellular links, still entirely in space, with latency bounded by delta. Only if both phases miss do we fall back to the ground station and the original ground station, and we cache this response for the next time. We have presented the spatial and the temporal coordination of scope. Now we ask the empirical question: how well does it actually work in flight? We evaluate the three properties one by one. The first one is observance. Does the cache ratio hold up under different handover intensities? The second one is service continuity. Can users perceive a smooth quality of experience over a real 15-minute Starlink trace with low latency clicks at handover boundaries? And finally is the cost benefit. Is the inter-satellite link overhead we pay reasonable compared to the ground satellite link traffic we save? All experiments use the real Starlink constellation snapshot and three competitive baselines. Now we move to the experimental setup. We built a discrete event simulator in Python, driven by real-world TLE data of the Starlink Shell 1 constellation at 550 kilometers altitude and 53 degree inclination. The FCL bandwidth between the sellers is bounded by the handover window duration, reflecting the real physical layer, nail time, and spectrum constraints. The workload follows the GPF distribution with skewness 1.3, and the content model includes both heavy head video objects and the long tail web and text objects. Inside each collaboration group, we use a single copy storage policy, so every handover can remove Unicode cache the data and stress the migration algorithm. We compare 4 strategies: no handover as the static baseline, set-based migration, and popularity-based migration, and scope, our spatial-temporal approach. We start with the orbital stress test. We vary in out the number of sellers leaving the groups from 0 to 6. Fixture 6 on the left shows the cache ratio. As more sellers leave, all strategies degrade because the lost Unicode data goes lining with N out and quickly stretches the FCL bandwidth. But scope stays remarkably fast. At N out equals 6, scope still keeps the hit ratio around 73%. And while popularity-based drops to 40% and set-based drops to 33%, and low handover close-based to 60%. Fixed 7 on the right tells the same story of latency. Scope's latency stays around 190 milliseconds, even at the worst level, while the baseline wants to bring 380 and 540 milliseconds. Why? Because site-based fills the bandwidth with unpopular junk files. Popular-based explores the bandwidth after migrating just a few large videos. Scope picks high value and bandwidth efficient items and therefore preserves performance. Now we look at the service continuity through a 50-minute time series trace in the US region. There are 3 handover events at minute 3, minute 8, and minute 13, with 1, 3, and 2 sellers leaving respectively. Fig 8 shows the real-time cache hit ratio. The baseline will show clear cliffs at each event. Hit ratio drops by 10 to 18 percentage points and recovers only slowly through the cache warm-up. The low handover line is the worst. It crashes below 60%. Fig line shows the real-time latency. Baseline spike past 220 milliseconds. Scope, in contrast, remains nearly steady across the entire trace. The hit ratio stays above 77% and the latency holds around 140 milliseconds. This is because Scope proactively migrates high-value density content while inter-cellular links before the physical handover. So entering sellers already serve users with warm cache and the moment they take over. Now the last metrics is the cost-benefit analysis. We measure FCL bandwidth consumption as the cost and the GFCL traffic offloaded compared to low handover as the benefit. Look at Fig 10. Site-based has the lowest cost because it has only 3.2 GB of FCL, but it also produces almost no real benefit, just 25 GB of GFCL offloading. Popularity-based has the highest FCL cost at 15 GB because it tries to migrate large video files. Yet its benefit is only 85 GB lower than Scope. Scope sits at the sweet spot with 10.5 GB of FCL bandwidth, moderates the cost, and it offloads 128 GB of GFCL traffic, which is the highest benefit by a clear margin. This validates that the value density-based selection truly maximizes the unity of every byte transport over the siloed consolidation. We have shown that Scope delivers strong empirical wins across operators, service continuity, and cost benefit. In this final part, let me consolidate the story. First, I will recap the conclusion, what exactly the seller CDN community should take away from this work. Second, I will briefly position Scope against the related literature. Most apparent RU's cache work is either per satellite or replication only, and does not explicit predictable orbital geometry. Third, I will outline the 3 future directions we believe are worth pursuing. The first is energy-aware migration with limited solar buckets. The second is inner cancellation cooperation across providers. And the third is resilience under partial intercellular links failures or DDoS conditions. The problem we tackle is the cache accident challenge in LU cellular CDNs, caused by two facts: high orbital mobility and very limited onboard storage. Together, we produce a cold start cliff at every service handover. Entering cells land with empty caches and user feel the pain. Our solutions go jointly optimize cache management around two dimensions. Spatially, it pulls the isolated storage resources while latency constraint grouping, so that nearby cylinders act as one logical cache. Temporally, it maintains service continuity through proactive content migration, driven by the value density metric. During the predictable handover windows, driven by real Starlink TLE, two-line element tracing, Scope delivers three results that matters to operators: a cache ratio above 77% and let holds steady through handovers, and a latency around 140 milliseconds with no cliffs at event boundaries, and over 50% of ground cellular link traffic offloaded. In short, Scope turns on the isolated, drifting the cellular cache into one CDN fabric. This brings me to the end of talk. Thank you very much for your attention, and I'm very happy to take any questions. To recap in one sentence, Scope is a spatial and temporal cache cooperation framework that keeps LU cellular CDNs continuous and efficient, more hits, and lower and smoother latency, and significantly less ground cellular traffic. I will be glad to discuss any aspect. Thank you.
Okay. Thank you for the great talk. Any questions from the audience? Okay, then maybe I can ask one while the audience prepare questions. So yeah, very nice talk. I'm actually wondering, so your collaborative caching approach, is it like these satellites transmitting their caches among each other through their network?
Yeah, that's the second phrase. The first phrase is to look up in its own cache.
Okay.
Yeah, and
so if their cache is, then they will go to their neighbors.
Yeah.
Okay.
Because it don't go to the ground.
Okay. Because in traditional CDN, right? So they, I think it's because traditional CDN is hierarchical. So I guess here you don't have any hierarchy. Do you have any hierarchy in your caching design, or there's mostly flat plus a ground CDN?
Ground CDN?
No, I mean the satellites. Do they have hierarchies among the satellites, or is it mostly a flat structure among the satellites?
Yeah, the satellites, the most feature is the highly dynamics. So the dynamics is very different from the ground CDN.
Okay.
That's why I designed for this, and they can look up from labels.
Okay, got it. All right. Any other questions from the audience? Okay, if not, let's thank the speaker again.
Okay, thank you.
All right, now let's go to the next talk.